In this video, we're going to talk about how to model geometric sequences. So let's look at an example of a real-world application of a geometric sequence. So a culture of bacteria doubles every 2 hours. If there are 500 bacteria at the beginning, how many will there be after 24 hours? So a key point to remember in these types of problems is to understand, are we starting at our 0 place or our first place, so a sub 0 or a sub 1. In this situation, the beginning, so no time has passed, we are starting at a 0 term. So if you want to think of it as a sub 0 is 500. And if we are doubling each time, then we know at a sub 1, so in this situation a sub 1 represents 1 hour, we will have 1,000 bacteria, and so on. So let's begin by writing our explicit rule for this situation. So using the subscript notation, we will say that a sub n is equal to our starting value. So for this example, we'll use a sub 0. So an initial value times the rate, the constant ratio, in this case double means we're going to be multiplying by 2 each time, raised to a power of n. So once again, our 500 is that initial value, where 2 is our rate, and then n represents the number of hours. Now if you wanted to write an explicit form or explicit rule starting at a sub 1, you would use 1,000 times 2, but instead of n, you would write n minus 1. So it all depends on, are we starting at a sub 0 or a sub 1. In this situation, in the context, it really makes sense to start at a sub 0. Alright, so from our explicit form, we can actually develop an algebraic rule. Many of you saw this in arithmetic sequences, but for explicit, so for arithmetic, the algebraic rule comes out to be linear, and you see that in the graph. However, for explicit, you'll notice it'll look very much like an exponential. So instead of a sub n, we will write y, and we will say y is equal to our initial value, so our a sub 0, times 2 to the x, where x is the number of years and y represents total bacteria. This is considered what's called an exponential growth model, and we'll refer to it as exponential model. So when our rate is a whole number, so not a fraction, it's considered growth. So it would be considered exponential growth. Whereas if we have the rate is a fraction, it would be exponential decay. So an exponential growth / decay model. So using a geometric sequence, we can set up an algebraic rule for this exponential model. However, we also have a specific exponential growth decay model that we use. And the general form of these exponential growth and decay models are a equals a sub 0, or we can also refer to this as a naught, times the quantity 1 plus r raised to a power of t. This is where a sub 0 is the initial value, r is my rate, and t is my time. So looking at the example, B invested $15,000 at a rate of 8% per year. So if I wanted to set up an expression or an equation for this, I would say y is equal to my initial amount So 15,000 times 1 plus the rate. In this situation, my rate is 8%. Now, it's important to remember that when you express a percent, that we convert it into a decimal, which we can do by moving the decimal in the percentage over twice, or dividing the percent by 0. Think of it per cent. Cent being 100, per being division. And so we would make our new r 0.08 raised to a t. And using this model, this equation, I can substitute any value for t to find a given amount. So the equation is expressed as the total amount in the account after t years. And using this, we can predict certain amounts or even time periods for when an amount will be achieved. So thanks for watching.